Okay, so without further ado, Brian Williams has kindly agreed to speak in our virtual seminar on superconformal factorization algebras and framed E2 algebras. Take it away, Brian.
All right. Thanks, David, and thanks to the organizers for inviting me to speak and all of those who decided to participate. Okay, so the title of my talk is maybe a little strange, something I call n equals 2 factorization algebras and framed E2 algebras. Maybe part of that title sounds familiar, but I hope to define all of those things throughout the talk. So the part that might be most familiar is this term E2 algebra or framed E2 algebra. Indeed, the sort of theory of EN algebras has appeared in a lot of the talks in the seminars and some of the courses that have been going on throughout the semester at MSRI, say in the context of say configuration spaces and factorization homology. But today I want to, so today I wanted to sort of tell you a way in which E2 algebras, so maybe in this context of configuration spaces, we thought about these EN algebras as arising from topological field theories or functorial field theories even. Today I want to talk about a way in which framed E2 or E2 algebras appear from a slightly different type of object, namely a vertex algebra with some extra structure. And these vertex algebras with extra structure are also motivated by physics. So I wanted to sort of start the first slide, which gives a little bit of motivation of where these objects are coming from. So hopefully you can see my cursor. Can people see where I'm pointing?
Yeah, it looks good. I can see it.
Okay.
Yep.
Okay. So in physics, the type of object we want to start with is something called an n equals 2 supersymmetric model. So this is all happening in 2 dimensions. You can all imagine this happening on some Riemann surface. So to any physical theory, we obtain a mathematical object called their local operators by looking at their observables. And the observables is well known in like a chiral CFT. We know they're described by vertex algebras. N equals 2 supersymmetric models aren't quite holomorphic or chiral CFTs, but they still do give rise to something akin to a vertex algebra. So roughly the observables look like some vertex algebra together with a sort of anti-holomorphic version of that vertex algebra. And they're sort of coupled in some interesting way in general. And the type of symmetry I want to keep track of here in this case is played by what's called the n equals 2 superconformal algebra. So this is the full symmetry algebra of some local operators of this n equals 2 supersymmetric theory. Now, as we go down in this list here, I think we're getting to objects that mathematicians are more and more comfortable with. So down one level, we can perform something that's called a twist of an n equals 2 supersymmetric theory to get to a place where a lot of us are comfortable with. That is a chiral CFT. This is just called the half twist. And we know a chiral CFT in general is described by a vertex algebra. But it happens that if the chiral CFT came as the half twist, what I'm calling the half twist of this n equals 2 supersymmetry, these vertex algebras have some extra structure. And throughout the talk, I'm going to refer to these either as a twisted n equals 2 vertex algebra or a topological vertex algebra. This terminology of a topological vertex algebra, I think, is going to be a little confusing, especially for those more in the world of EN algebras. But I just wanted to point it out that that's sometimes what these objects are called. And what is the sort of defining characteristic of these type of objects here? Well, it's their symmetry algebra again. And they have a symmetry of what's called the topological Virasoro algebra. And this topological Virasoro algebra you can think about as coming as well as some procedure like a twist from the full n equals 2 superconformal algebra. Now we can go further down this chain and consider what's called the full twist. Oftentimes people just start with the n equals 2 theory and consider the full twist, but it actually factors through this chiral theory. So from this chiral theory, we can consider a full twist and get down to an object that a lot, maybe even more of us are comfortable with, that is a topological field theory. And these topological field theories, upon taking their observables, give rise to E2 algebras, or sometimes framed E2 algebras as well. And depending on which one I said here, you also want to keep track of a symmetry algebra, which is the rotations of the disk, which is SO2. Okay. So the type of construction I really wanted to hone in on during my talk today is the following. So there's this classical construction of Gerstenhaber or BV algebra, depending on whether or not I said E2 or E2 framed here, from the data of a topological vertex algebra. Now, Gerstenhaber in BV can be realized in more familiar terms as the cohomology of either the E2 or E2 framed operands. Rather, algebras, Gerstenhaber algebras and BV algebras are algebras over the cohomology of these two operands here, which have other names which go by the P2 operand in the E2 case, and this BV operand here, cohomology of the framed E2 operand. And there's a sort of well understood construction from the data of a topological vertex algebra that factors through the cohomology, sort of cohomology of this topological vertex algebra that gives rise to objects of this form, either Gerstenhaber or even BV. My goal today is to sort of describe an enhancement of this construction, which doesn't just give rise to something at the level of cohomology, that is these types of Gerstenhaber or BV algebras, but actually gives rise to a cochain description that is a description at the cochain level, which is really the structure of an E2 or an E2 framed algebra from the data of a topological vertex algebra, which I've been calling TVA. And my sort of main ingredient is to use the theory of factorization algebras, maybe most closely related to the approach of Costello and Gwilliam. Okay. So are there any questions about this sort of, this is sort of the general goal of the talk. Are there any questions? Maybe I'll pause for.
Sorry, Brian, I missed,
Yeah.
You talked about a topological vertex algebra. I'm familiar with the vertex algebra. I don't know quite what you mean by topological vertex algebra.
Yeah, so I'll define it in a few slides, but what I mean is a vertex algebra here that has the symmetry by what's called the topological Virasoro algebra.
I see, okay.
Yeah.
So this is Ezra.
Hi,
so hi. So I'm not sure I'm pronouncing his name right, but Juan in Rutgers has been working in an analogous direction for a long time. So I'm wondering if, in what way your work is perhaps related or perhaps distinct from what he's been trying to do.
Oh, I think it's completely related. The type of construction I really have in mind is sort of most closely motivated by the models that I want to work with. So really I have models, the type of models I'm most familiar with are these factorization algebras. So I'm really going to give a construction sort of purely in those terms. But I totally agree that there are models that sort of lift this description at the level of cohomology to some infinity structures at the cochain level.
Well, he's no topologist. I don't think he has ever really referred to the topology in his work. He probably only looks at like n equals 2, if at all, and not at the topological twist. But I'm just curious if, you know, if there's any overlap. But
I think the underlying objects will end up being equivalent. I think what I'll do is provide a. I view what I'm doing as a more geometric description, whereas he's sort of really doing algebra. Yeah.
Yeah. Okay. Cool. Thanks.
Thanks. Okay. So maybe I just wanted to give some examples for why I care about these things. I'm not going to talk about any of these examples in the talk, but if I say any terms that sound interesting to you, I'd love to talk more about any of these examples. So the first one is sort of maybe an extended version of the diagram or a more specific version of the diagram that I just drew in the first slide. So starting with n equals 2 supersymmetric sigma model, we know very well how to obtain two topological theories called the A model or the B model. These arise from two different twists of an n equals 2 theory. Now, actually, these topological theories factor through chiral CFTs that I'll just call the half A twist and half B twist. And each of these chiral CFTs or vertex algebras carry the structure of a topological vertex algebra. And sort of roughly, you can imagine the half A twist. It's what you would consider as the chiral version of the de Rham complex, which I want to think about, say, as the Hochschild homology of functions on a manifold X. And you can think about the half B twist as a chiral version of Pauli vector fields, which is the Hochschild cohomology. So each of these structures, these half A and half B vertex algebras, have topological structures. And so in this way, I would be giving, the construction I have in mind would give rise to the usual E2 structures or Fran D2 structures you have in the local operators on the A and B side. Cool. Sort of in a more general direction, you can show that if X is any -1 symplectic space, and I'm going to say a word that I probably won't talk about for the rest of the talk, there's a vertex algebra you can associate it to it called the chiral differential operators on X. So really everything is automatically derived here. To even talk about -1 shifted symplectic spaces, I need to be working in some derived world. But you can define what's called chiral differential operators on X, some sheaf of vertex algebras associated to X. This object has the structure of a topological, really a sheaf of topological vertex algebras. And this line of work is sort of pretty new work, and it's joint with Pavel Safronov. So I'd love to, if anyone's interested in that, we can talk about that later.
You said it's a sheaf of topological vertex algebras on X, or?
On X, yes, yeah. Sorry, that was not so clear. Yeah. In the last class of examples, sort of go by the name of string vertex algebras. They're called string vertex algebras because it's these vertex algebras that arise from quantizing the various versions of the string. And there's even supersymmetric versions as well. So roughly, you're studying maps from a Riemann surface into some target manifold X, while at the same time coupling to sort of diffeomorphisms on the source manifold sigma. And in general, these types of string vertex algebras have the following flavor. So you have some sort of base vertex algebra, namely that I'll just call the CFT. That's like the vertex algebras associated to sort of theories of maps of this form, sigma to X. And then you also have this ghost vertex algebra. This ghost vertex algebra describes the local diffeomorphisms of the Riemann surface. So this is what's really giving rise to the string part of the terminology here. I'm coupling to the local diffeomorphisms on Riemann surfaces. And in general, these vertex algebras also have topological vertex algebra structures. And an application of this type of the type of thing I have in mind today is to use the description I'm giving to describe a BV structure, the BV structure that I'm talking about today, to obtain a QFT, not on the source Riemann surface, but really on the target X. This is one application of the thing I have in mind today. And you can view this as sort of a mathematical version of what physicists call string field theory. But again, I'm not gonna talk about that at all today. It's the last time the word string will appear in the talk. But if anyone wants to talk about that further, I'd be very keen to discuss.
So when you talk about a QFT here, I mean something different than a CFT or a TFT?
Yeah, so QFT in this very last line I think you're referring to, it's actually a QFT. So when I'm talking about these vertex algebras, I'm really thinking about them as arising from CFTs, which are special types of QFTs on the Riemann surface. Now you can use the data of this vertex algebra to cook up a QFT actually on the target manifold X. This is not going to in general be a CFT because X is any type of target manifold. It's not just in general, it won't just be a Riemann surface. It could be some higher dimensional, say, Calabi-Yau manifold or something like that. And really what the the data that I'm outputting here would give you a way of concocting a QFT on this manifold X from this data.
Okay, thanks.
Yeah. Okay. There are no more questions. We will move on to the. Oh, yeah.
If you fix sigma, but you vary x, is there some? You said you get a QFT for each x. Is there some sort of compatibility of the QFTs on different x's that you obtain in this way?
Some sort of compatibility. I'd say it is natural. It is natural in some sense on the target X. Maybe I don't quite understand, but there is some naturality in the target here, at least for the type of perturbative theories that I'm thinking about. Yeah.
So is saying that it's a QFT on X in particular saying it's natural with respect to opens in X?
It is, yes. Yeah, it is. Though the way in which I'm constructing that naturality is not clear from what I've said so far, but it is, yeah.
Okay, yeah, I think that was my question. Thanks, David.
Oh, well, but I thought David's question, this is on Francis.
Hey,
I thought David's question was if X was like a Calabi-Yau, but you varied the holomorphic structure or something like that, do you obtain some kind of connection over the relating the QFTs?
Yes,
that
you
could
do.
have been my question.
Yeah, yes, you do. Yeah, I think that's a related. Yeah, yes, you do. If it's okay, if that is something you're interested in, maybe we can discuss it after the talk, because I don't think it's going to play a role.
Sounds good.
Okay. Okay. How do I go forward? Okay. So I just wanted to set up some terminology here. Maybe a lot of you are familiar with the theory of vertex algebras, but I sort of need a slightly enhanced version of what people usually refer to as vertex algebra, that is to put in the word DG everywhere. So let me just briefly sort of say what I mean by this type of object here. And I could also put in the word super, but let me not worry too much about that here. So a DG vertex algebra is this sort of tuple of data. Here, the first two pieces, V and D, define the structure of a cochain complex. Everything's going to be C linear for me. This operator del, it's a cochain map from V to V. It's called the translation map. Really is from the geometry of the Riemann surface, or really this is just about the Riemann surface sigma equals C, flat space. This is really generating translations on flat space, holomorphic translations. And really the juice is all in this element Y, or this object Y, which is a cochain map of this form. So V goes to endomorphisms of V valued in some Laurent polynomials in Z. And the sort of standard vertex algebra notation is to write it sort of expanded in this form as a power series, as a Laurent series in Z. So here A is an element of V, and in this expansion, we get all of these A sub n's, which are each endomorphisms of the original cochain complex V. And the sort of interpretation here is that for elements A and B, we want to think about these A n sub B's as a way of multiplying elements here. So this gives you a new element of V. Of course, in an ordinary algebra, associative algebra, we have one way of multiplying, and in this sense, we have a whole integer's worth of multiplying elements. So that's all sort of standard in the usual way of thinking about a vertex algebra. I've just sort of put in the words DG everywhere. So there's some obvious compatibilities that I won't go too far into. Like I said, this del operator really plays the role of translations, which you see in this condition here. And there's also a very important associativity condition for Y that I won't state. but it's the standard one if you've seen open any book about vertex algebras. So there's a very important example of a vertex algebra, maybe a boring example. There's a notion of commutativity of a vertex algebra. And this says that all of these endomorphisms, A sub n, are all 0, as long as n is bigger than or equal to 0. And you can show that in this case, this operation that sends two elements A and B to the element A minus 1 operation with B actually endows the entire cochain complex with a commutative DG structure, commutative DG algebra structure. So this is sort of a boring example of a vertex algebra, but maybe just to give you a hint at what this associativity is condition in the special case is saying that this product ends up being associative. Okay, next page. So there's a useful sort of organization that I'll use. It's totally standard in vertex algebras. It also works just as well in this DG setting, which is the operator product expansion. So it's a way of describing a product of these two elements here. So remember these A of Z and B of W, it's an alternative notation for Y applied to the element A and Y applied to the element B. So part of the axioms of a vertex algebra that I didn't spell out completely tell you that these types of products actually have this really nice form. So they all look like sums of elements of this form here. So these CK of Z's are again elements of this vertex algebra. They appear with this particular power of the difference Z minus W. Plus you have all this other stuff that's actually regular in the difference Z minus W. And the sort of standard way that physicists, this is borrowed from physics, of writing this type of formula here is to say that A of Z times B of W, the symbol sim, to the sum here, where you just forget about the regular part of Z and W, of Z minus W. And there's a nice way of summarizing commutativity here, which is to say V is commutative if and only if this expression here is called an operator product expansion, OPE, if and only if these OPEs are all trivial. Okay. So far, so good. I just wanted to do a very basic example of one of these objects here, sort of fundamental for the rest of the talk. And that's called the Virasoro vertex algebra. So the Virasoro vertex algebra is built from the Virasoro-Lie algebra. So the Virasoro-Lie algebra, what is it? Well, really it's a central extension of vector fields on the punctured disk, the punctured holomorphic disk, which I'll choose to parameterize in this way. So we have these LNs, which are all given as powers Z to the n plus 1, d by dz. N can be any integer here. And we also have this central extension term, central extension element C. So there's a Lie bracket here that gives rise to the Virasoro-Lie algebra. And there's a very important representation of this Virasoro-Lie algebra that I'll call Virsa plus. And it's spanned by, sorry, I should have said spanned here. These elements L sub n, when n is bigger than or equal to -1, and also this element C. And there's the vertex algebra. So far, these are all about Lie algebras and their modules, and you get the vertex algebra by the following construction here. So this is sort of an induced module construction. So you take the one-dimensional vector space C, you endow it with the structure of a Vir plus module. Oh, sorry. Where this module structure here says that, well, all of the LNs act trivial, And this central element C acts by multiplication by little c here. So this makes sense for any little c in the complex numbers. This is called the central charge. So this is a parameter that is left over in the definition of the Virasoro vertex algebra. So what you do is you induce up from this Vir plus the sub-Lie algebra to a module for the full Virasoro Lie algebra, take its enveloping algebra here. So this is called the Virasoro vertex algebra at central charge little c. And if I wanted to write it in the sort of field notation that I was writing down before, where I had these OPEs written down, usually write L sub z is this sum here. So these L sub n's play the role of these endomorphisms of the which was part of the sort of data of the vertex algebra that I had originally defined above. Okay. So there's nothing new here, but if there's any questions, maybe I'll pause for 30 seconds. Hopefully this was.
Can you help me understand? This is David Ayala. Can you help me understand what you mean by here L is, and then there's an expression? I don't see.
So sorry. So the LNs here were defined above. Those come from the generators of the Virasoro Lie algebra, and the sort of to match with this notation that I was writing in the. How do I go up? To match with this notation here, I was just setting up sort of a convention for what I mean by y of z, or y of a comma z here. These
that's right.
These cochain maps that define the structure of a vertex algebra.
Oh, got it. Got it. Thanks.
So there's this shift here, minus n minus 2. In the definition of Ln, but this is sort of a standard convention that people always make. Okay. Okay. So before talking about superconformal algebras, the Virasoro is useful because it lets us define the notion of just a conformal vertex algebra. So a conformal vertex algebra in terms of physics is the structure of the operators of a conformal field theory, a chiral conformal field theory. And there's a nice way to say it in terms of the Virasoro, which is it's a vertex algebra V together with a map from the Virasoro vertex algebra at some central charge C. So part of the data of a conformal vertex algebra is this number C. And this gives us a lot of structure on the vertex algebra V, this data here. Part of that data is a nice sort of grading on the vertex algebra V. And that grading comes from this rotation vector field. So L0, remember, was, in terms of geometrically, L0 is z d by dz. So this is like rotations of the disk. And we define this grading of the vertex algebra V by saying V sub n, or all the elements in V that have eigenvalue n under L0. So these are called this n is called the conformal weight. So these comprise all of the elements of conformal weight n. Okay. So that was all sort of very standard terminology, I hope. Now, I'm going to use this conformal weight to sort of organize a lot of elements later on. So that's why I wanted to get that out of the way. And now we can move on to defining what I call the topological Virasoro algebra. Great. So the topological Virasoro algebra, you could think about as being an extension of the ordinary Virasoro algebra. So this is really motivated by, I would say, by supersymmetry, but I'm not going to mention supersymmetry here at all. So the topological Virasoro algebra, well, it's a vertex algebra. It's actually z-graded. So before everything, I said all my vertex algebras were DG, but everything so far was sort of concentrated in degree 0. The topological Virasoro has an interesting z-grading. And I'm just gonna, instead of giving you the full definition, I'm gonna sort of give you the generating elements of this vertex algebra. And I'm gonna sort of organize them by both their conformal weight This is this decomposition here. And their cohomological degree. That's the Z grading here that I'm referring to. So there's 4 generating elements. They just have, I'm just giving them these names to try to match with the literature. So we have this element L. This is actually the same L as in the definition of the Virasoro algebra. It has the same conformal weight and it's in cohomological degree 0. There's an element J. It has conformal weight 1, cohomological degree 0. If you're familiar with other types of vertex algebras, just this J on its own generates a vertex algebra called the U1 Kac-Moody vertex algebra. There's another element Q. It has the same conformal weight as J, but it has cohomological degree 1, +1. And then there's an element G. It has the same conformal weight as L, but it has cohomological degree -1. So to really define for you what this vertex algebra is, I would have to sort of tell you what all the OPEs are, if you like. That's one way of doing it. Instead of doing that, I'm just going to sort of list off a few important OPEs to try to give you a sense of the structure here. So there's this OPE between L and itself. It's of this form. Now, I didn't tell you what the formula was for the OPE in the Virasoro, but for those that are familiar, they can recognize this as the usual description of the Virasoro vertex algebra, but it has central charge 0. So the L's generate a Virasoro vertex algebra of central charge 0, C = 0 in the above notation. There's some other OPEs here that I'll just list based on whether, I think might use some of these later on. So the next one is that it says the self-OPE of Q with itself is 0. Q commutes with itself. And also, there's an OPE between Q and G of this form here. So this may not mean too much to you, but I wanted to just point out that you see in the OPE of Q and G, there's an appearance of L on this right-hand side. L, remember, generated the Virasoro algebra, these vector fields on the disk. So this is going to play a role in a minute. And you notice there's another parameter involved here that I've called D that appears in this OPE, for instance. It appears in a couple of the other relations as well. This is called the topological central charge of Vir. So I really should have labeled Vir upper top with the letter D. It also depends on this parameter, this complex number D, but that won't play too much of a role later on. So for those of you familiar, that's where it is. And this is again sort of a boring DG vertex algebra because I haven't turned on any differential here. This is just a Z-graded vector space. Vir itself as an underlying cochain complex has 0 differential. Okay. And I wanted to point out sort of a consequence of at least the OPs I wrote down. So the first consequence is that if I look at this, the 0 part of Q, so when I write this sub-0 here, I'll refer to this as the 0 mode. This is because Q of 0 appears as the sort of 0 Fourier mode in that expansion that I wrote down. So the 0 Fourier mode of Q, well, it's an endomorphism of the underlying vector space. It's an endomorphism of cohomological degree +1. And that OPE condition tells you that it squares to 0. And that second OPE condition, the second OPE that I wrote down, tells you that this 0 Fourier mode of Q extends this field G, the commutator with the field G, is this Virasoro field L here. So what is this telling you? Well, it's telling you that L of Z is actually exact for this differential Q sub 0. Q sub 0 really defines a differential of the cochain complex. That's what this condition says. And it tells that all the Virasoro fields are actually exact for that differential. Okay. But so far, when I say topological Virasoro, I don't mean that I'm turning on this differential at all. It's just there as part of the data. Okay.
Brian, this is David Ayala
David.
again. What's the relationship between topological Virasoro and Virasoro? It might just be obvious, but if you could say, that'd be great.
Oh, I think so this definition of topological Virasoro is really motivated by a supersymmetric version of the Virasoro. And a supersymmetric version of Virasoro means some super vertex algebra, which is an extension of the ordinary Virasoro. An extension means we're throwing in a bunch of maybe more even or more odd fields to the vertex algebra. But they all had this property that they had been a map down to the ordinary Virasoro algebra. So that's why Virasoro keeps appearing. Yeah.
Thanks.
Yeah.
So is one of the points that when you consider modules over some conformal VOA that they're kind of graded by L naught, that you're going to want this Q to introduce like the differential on modules over your topological version.
Exactly. That's exactly where. Yeah, I'm going to get to that in a second, but that's exactly what we're going to do. Yeah. Sorry, maybe I interrupted you, Chris. Sorry. Did you have a follow-up?
Nope, that's good.
Okay. Okay, so in the analogous case of a conformal vertex algebra, I can now define this notion of a topological vertex algebra. I pointed out on the very first slide that sometimes people call this a twisted n equals 2. But since this n is referring to supersymmetry, I'm going to try to avoid talking about supersymmetry. So I'm just going to call it a topological vertex algebra. That's actually going to come back to bite me in the butt later on. I will actually use n equals 2, but for a good reason. A topological vertex algebra, well, it's a vertex algebra V. Again, when I say vertex algebra, I mean DG, possibly just graded, together with a non-trivial map of vertex algebras from the topological Virasoro vertex algebra that I just sort of sketched above to V. And as Chris just pointed out, what I can do with this data here, is I can use Q sub 0 now. I can now view Q sub 0 as an element of V via this map to define a DG vertex algebra structure. So maybe it would probably have been more accurate for me to say, if V itself had an internal differential, what I'm doing is I'm deforming that differential by Q sub 0. So here, the way I'm writing it here, I'm imagining V as just some graded vector space. And I'm introducing a differential, but in general, you can imagine it as deforming the differential. And
so non-trivial here means Q goes non-zero?
Yeah, just because I want some
what
interesting examples. That's right. Yeah. Oh, sorry. Go ahead, David.
That's okay. You answered my question.
Okay. Right. And part of the sort of axioms of the topological Virasoro here tells you that this is indeed a DG vertex algebra, this new object here. So what Leon and Zuckerman and Huang, as Ezra mentioned in the introduction, they have a very nice construction, which is from this DG vertex algebra, they take its cohomology. Well, this is again going to be a vertex algebra, but it's actually always going to be commutative. In fact, it has a much richer structure than just a commutative algebra. It has the structure of a BV algebra. So here I'm calling the cohomology A. Let me just remind you briefly what a BV algebra is. So BV algebra, well, it's a commutative algebra. So you have this commutative product. You also have a bracket of cohomological degree -1. This is like a Poisson bracket, but it's shifted in its grading degree. When I say that, I mean it satisfies some satisfies some derivation, some Leibniz property with this commutative product here. And you also have this thing called a BV operator that I won't spend too much time defining, but this is again a cohomological degree -1 object from A to itself. So the first two are usually what are called Gerstenhaber algebra, and the extra structure of a BV algebra is the existence of this operator BV, delta BV. And their construction is sort of very, very concrete. They tell you exactly what each of these structures are, what each of these pieces are, in terms of the original vertex algebra structure. So the commutative product is no surprise. This is what I said before. In any commutative vertex algebra, this -1 operation gives you a commutative algebra. So that's this commutative product here. And then both the bracket and the BV operator use the structure of the topological Virasoro algebra. So it uses this element G and its 0 mode to define the bracket. And it uses the element G and its 1 mode to define the BV operator. And now I can sort of say more precisely the goal here. Well, BV, I think this has come up maybe once or twice in some seminars so far this semester. You could think about it as being the cohomology of this familiar frame D2 operad. What I want to do is I want to lift this structure, this frame D2 structure, not to the level of the cohomology of V, but to actually this DG vertex algebra of V with Q sub 0 itself. So that's sort of my goal for the rest of the talk, unless there's any questions. Maybe I'll move on. Cool. Okay. So my main ingredient to do this is going to be to work more geometrically, and is to use the notion of a factorization algebra, along with some nice relationships that we understand very well, relating factorization algebras to both vertex algebras and E2/frame D2 algebras. So factorization algebra is a very general concept. It makes sense on any manifold M. And roughly, you can think about it as being an assignment for any open set. Here, you can replace cochain complex by any symmetric monoidal category, but I'm going to just live in the world of cochain complexes. That's what matters to me here. So it sends an open set U to F sub U, and all of, as I said, these are cochain complexes. I'm going to denote the sort of internal differential here, usually by D sub F. Additionally, there's the following data. Whenever you have some open sets that are disjoint, say U and V here, sitting inside the bigger open set W, you have the data of these maps from the tensor product of F of U and F of V to F of W. And you have this for any sort of arity of disjoint open sitting inside of some bigger open set. And there's some sort of obvious associativity condition you can ask for that these sort of product maps satisfied. And there's also a very interesting gluing condition that I won't mention at all. So I want to point out that there's a notion of a group action on a factorization algebra. We're going to use that pretty extensively. So roughly, you can think about this group action as saying, well, I know how the group acts on the value of the factorization algebra in any open set. And I want all of those actions to be compatible with embeddings of open sets and compatible with these product maps here, these factorization structure maps here. Hopefully that notion is clear. For the rest of the talk, mostly M is going to be Rn, really R2. And there's a special group action that I'll care about, and that's going to be called a translation invariant factorization algebra. And that's when you have this group action by the translation group, Rn. And I want to point out that this is a really nice Lie group. Whenever you have an action by this Lie group here, we get an action of this Lie algebra, which I think about as being spanned by, sorry, that should say span again, the constant coefficient derivatives d by dx1 all the way up to d by dxn. X is just the coordinate on it. All right. And these act by derivations of the factorization algebra. I'm not going to define that right now, but hopefully that's the notion is okay. Is there a question? Someone?
Hey, Brian, this is Aaron. Oh. I do have a question, actually. This is with respect to a group action on the manifold, right? It's so not just abstractly acting on the chain complexes after the fact.
That's correct, yeah. So this, okay. I mean, in this example, it does arise from an action on the manifold. Yes, that's right. Yeah, right. Hence why
that could be trivial, but in this case, it's the action of the group on the manifold.
Exactly, yeah. And I'm sort of going to be implicitly using that compatibility. Yeah. Yeah.
Cool. Thanks.
Yeah. Okay. So there's a.
Oh, can I just ask? So systematically, we should expect that you use M for the world sheet and X for the target in nonlinear signal models.
That's right. Yes.
Something like that. Okay. Good.
Yes. Thank you. Okay, so there's a nice sort of special case of this where you can ask for some extra structure. So when n is even, there's a notion of a holomorphically translation invariant factorization algebra. Well, it's a translation invariant factorization algebra. That's like one up here where you have an action in particular by all these derivations. But I also require the data of endomorphisms of the factorization algebra that I call eta bar, which trivialize half of the translations, namely the anti-holomorphic translations. So the terminology is such because whenever I have such data, the anti-holomorphic translations act homotopically trivially. They act trivially according to this differential, this internal differential of the factorization algebra. So this is an extra, this is extra data that you have on a translation invariant, that you can ask for in a translation invariant factorization algebra in even dimensions. Okay. Sorry. There we go. Sorry. Okay. So there's a really nice relationship between translation invariant, holomorphic translation invariant factorization algebras. Really, you actually have to require a little bit more structure on this, but I won't mention that. In the case that n equals 2. So these are like holomorphic factorization algebras on C or R2. And Costello and Guillaume have produced a functor from this category of such factorization algebras to the category of vertex algebras. And roughly what it does is it sends one of these objects F, these factorization algebras. What you do is you take a disk D, say centered at the origin. It doesn't really matter where it's centered because it's, well, translation invariant. But say it's centered at the origin. You take the value of that factorization algebra on the disk, and then you look at its cohomology. And very roughly, the way that you could recover the vertex algebra structure here, so really remember the juice was all in this operator Y. Well, this operator Y, remember it depends on this variable Z, you can think of as arising from the following factorization structure map. So what you do is you take one of the elements of the factorization algebra on a disk. So you take one disk that's centered at the origin here. You take another disk that's centered at Z. Z here you can think about as being some formal parameter now, because I'm going to let it be any non-zero number. What you do is you look at the factorization product between those two disks. That sits inside of a bigger disk. So again, looks like F applied to some bigger disk. And if you do this in a smart way, you can exactly recover the data of Y, and it's a little more work, you recover the full data of the vertex algebra. So this is really putting sort of putting light to this way of thinking about vertex algebra, which is as a family of multiplications parameterized by some formal variable z. Okay, so it's really nice. There's another notion that's sort of it's a more general than this holomorphic translation invariant. Sort of nice to point out here. If I have an action by a group, I say that this actually is an action by G Theorem of that group. So here Theorem means, you can think about, if you're familiar with stacks, is really I'm thinking about this as the Theorem stack of the Lie group G. But I'll just tell you what this means very precisely. Well, I'm going to say this happens if the Lie algebra of G, so of course I have an action by the Lie algebra of G by derivations on the factorization algebra. If this Lie action is homotopically trivial. So really I would try to, in practice, I would actually ask for data like the way I did for holomorphic translation invariants. So what does that mean? Well, it means that for every element of this Lie algebra, X, I have a derivation, eta of X, which trivializes X according to the internal differential of F, the factorization algebra. So this is really a more general case of this holomorphic translation invariance. So it's a really nice theorem. I sort of view this as maybe an alternative to Laurie's famous theorem, which relates locally constant factorization algebras in Rn to En algebras. This is sort of engineered to work in a slightly different situation where I have different data on a factorization algebra. And that's really the type of data I'm going to be cooking up today. And this is due to Elliott and Safronov. So there's the following.
Sorry.
Yes.
Sorry. Yeah. Well, what's in the case n equals 0? So I've just wanted to know, what is the underlying category of objects that you're looking at algebras in?
N equals 0. So the category, my target category is the symmetric monodal category of cochain complexes.
With which grade? I mean, what grading? That's okay. That's going to be my question. So over which field or ring?
Everything is over the complex numbers for me.
Over complex numbers, and with which is bounded below, bounded above, bounded, unbounded? Which one?
There's no bounding. It's unbounded. Yeah.
So they're working with the category of unbounded cochain complexes.
Yes, and I really need to be careful with what tensor product I'm using. I'm not going to say too much about that, but there is a way to make it work where you use a completed tensor product.
So there is a symmetric monoidal structure on unbounded cochain complexes.
Yes, yeah.
And that's all explained in their paper.
This is all set up in the book of Costello and Gwilliam. Yes, yeah.
Oh, so okay. Could I ask which section? Because
so it's in the appendix. It's in the appendix of book 1, which is published now in Cambridge University Press. Yeah.
I see. Appendix of book 1, and yes. It is an infinity category. They show that it's a symmetric monoidal infinity category.
They do produce an infinity category. Yes. Yeah.
I see. Okay. Thanks.
Yeah. So this is sort of a recognition. This is a sort of an alternative to the recognition principle of Lurie of En algebras as locally constant, but given slightly different data. And this is due to Elliott Safronov. So there's the following equivalence of categories. There's 2 sort of flavors here, corresponding to framed and unframed. So the first is you look at factorization algebras on affine space, together with an action of Rn de Rham. Remember, that means that all translations are acting homotopically trivially on F, together with one extra condition. It's this condition that this embedding of disks here, if I have one disk embedding inside of a larger disk, this is a quasi-isomorphism. This is equivalent to En algebras. And there's also a notion for framed, where I use a slightly bigger group here. So instead of just having Rn de Rham act, I actually have SON semi-direct product Rn de Rham act. So this is really giving me this extra data of a framing on this side.
Hey, Brian, this is David Ayala. So I'm curious. I know this is not your result, and if you want to just defer to theirs, that's fine. But is there a way to codify that second condition in that first equivalence, namely the change of little r to big R, in terms of just modifying the group a semi-direct product with R cross by scaling and Rn de Rham?
I think something like that is true. Yeah, I mean, I could probably try to answer that if I look at their paper, but it might be good for me to just like show you that reference, and maybe we can talk about it. Talk about it after. Yeah.
Okay.
Yeah.
David, this is Aaron. I sort of follow up. Are you pointing to the difference between like a literal group action and then a bunch of quasi-isomorphisms?
No. No. In the double underlined and, the first time it appears in the two statements of this theorem, after the and, it says there exists. I guess the map is given, and the condition is that it's an equivalence as you change little r to big R. And the infinitesimal version of that could be potentially codified by a different Lie group.
Exactly. Actually, so I actually will use that sort of. They do have a follow-up result of that form, and I'm actually going to use that. So it's like this action by dilations that I think you have in mind.
Exactly, by R cross. Yeah, exactly.
I'm gonna use that later. That's a really good question.
Okay.
I probably should have referenced that here, but yes.
Okay. Thanks.
So how am I doing? Yeah. So maybe I'll move on to the next slide. Okay. So now I can say my goal more precisely. So my goal is to develop the following notion. I'm going to call this a twisted n equals 2 factorization algebra. If I was literally following the pattern of terminology that I had in the first part of this talk, namely in the part about vertex algebras, I would call this a topological factorization algebra. That's a very terrible terminology here, because these factorization algebras themselves are not equally constant. So in the same way, topological vertex algebras, they're really interesting vertex algebras. They have interesting OPEs. So I don't want to confuse that notion at all here. So I'm going to refer to these as twisted n equals 2 factorization algebras until I can come up with a better name. So I'll call these there's a category of such that I'm going to define in a minute that I'll call fact upper n equals 2. And these all exist just on the. There's a notion that exists on arbitrary Riemann surfaces, but I'm just going to consider the Riemann surface C. So what's one property of these? Well, they sit inside of holomorphic factorization algebras on C. So in particular, they determine vertex algebras. And I'll call, in the diagram below, I'll call these holomorphic factorization algebras fact upper Hall. So this is the kind of picture I'm aiming for. So at the very top left, I have these holomorphic factorization algebras. By Costello and Gwilliam, they define vertex algebras via this functor, vert. Sitting inside of these is the object that I'm going to define in a second, are these n equals 2 factorization algebras. Well, they sit inside as a subcategory. So again, I can apply vert to obtain a vertex algebra. But in fact, we'll see that they actually define topological vertex algebras, or what I was calling the alternative terminology is these twisted n equals 2 vertex algebras. These are vertex algebras with this action by the topological Virasoro. So these are going to be cooked up in such a way that this statement is obvious, that this functor is obvious. Now, the interesting bit is to apply this result of Elliott and Safronov. So what I'm going to do is define a construction. It's going to be a functor as well from these n equals 2 factorization algebras to the style of factorization algebras that appear in the theorem of Elliott and Safronov. So these are these de Rham trivial factorization algebras for the group SO2 across R2. on C equals R2. I'll call this functor just by putting a tilde on top of the F later on.
Hey, Brian,
and then, oh yeah, go ahead.
Why is the map from vert upper top to vertex an inclusion?
So remember the way I defined topological vertex algebra was a
right.
vertex algebra with some extra data.
That's right.
Yeah. So
that seems like there could be a multitude of that data on a given vertex algebra.
Oh, that's totally right. I should not have put inclusion. There are definitely, yeah, that's right. Thank you.
And yet, are we still expecting fact upper n equals 2 to include into whole fact upper whole?
That is the same mistake.
Okay, gotcha. Thanks.
Yeah, that should be that should just be functors. Yeah.
Gotcha.
These are really forgetful functors. I'm sorry. Yeah. Thanks. Thanks. Okay. So then once we're down in this bottom left, I'm going to use Elliott and Safronov to produce these E2 framed algebras, these framed E2 algebras rather. And what this does is this exactly lists this construction of Leon Zuckerman and Huang. Well, from a vertex algebra, remember we could take its cohomology with respect to this Q0 to obtain a BV algebra. We also obtain a BV algebra by taking the cohomology of this framed E2 algebra here. And the claim is that all of these commute. So this object I produced down here, or over here if you like, is going to be a model, a cochain model for these BV algebras. So that's sort of the big general picture. And maybe I'll pause here for 30 seconds. But after this, I'll move on to discussing this notion of an n equals 2 factorization algebra. Okay. So like I said above, really this notion is sort of uniform on any Riemann surface, at least the definition of an n equals 2 factorization algebra is. So let me just define it on a Riemann surface. In general, we'll specialize to flat space in a sec. So the first thing I'm going to do is define the following sheaf that I'll call T sub n equals 2 of DG Lie algebras on a Riemann surface sigma. So what I do is the following. I use a formal parameter epsilon of degree -1. I look at this Dolbeault complex. So here T10 is the sheaf of holomorphic vector fields, and I look at its Dolbeault resolution. This is really a resolution for the sheaf of holomorphic vector fields. And I adjoin the parameter epsilon here. So you can think up to Hamitop, all I'm doing is looking at holomorphic vector fields adjoin this parameter epsilon. I really need to use this free resolution. It's going to be important for my constructions later on, but morally you can think about it that way. But I also have another piece. I look at the Dolbeault resolution of the trivial bundle. So this is just resolving holomorphic functions on sigma. I adjoin the parameter epsilon. And I also think about this guy as living in a cohomological degree shifted by 1, which I'll just use the notation d by d epsilon for that. That's going to be useful to think about in that way in a sec. So think about this as really being an odd vector field, this d by d epsilon, a vector field of degree +1. So I have these two pieces. Well, I told you there's a Lie structure here. Well, the DG structure is sort of implicit. I have the Dolbeault operator acting everywhere it makes sense. What's the Lie structure? Where are the brackets? Well, there's the first class of brackets is just the sort of standard one that you have for holomorphic vector fields, where I also sort of adjoin this parameter epsilon. That's no problem because this is a commutative algebra. I can always tensor commutative algebra with a Lie algebra and get a new Lie algebra. So there's a class of brackets that just look like the Lie bracket of vector fields. The remaining brackets act in such a way that's obvious from this notation here, this d by d epsilon. So let me just spell that out. So first I can take a holomorphic vector field. So H here just denotes a Dolbeau form, if you like. I'm sort of working locally. So I can take a holomorphic vector field and look at its bracket with something like this. This is now a function, holomorphic function times this odd vector field, plus this odd element epsilon times a function times this odd vector field. So really this guy in total is actually an element of degree 0. And it has this following bracket. So if you follow this formula, you see that epsilon and d by d epsilon are sort of acting in the obvious ways. So for instance, what's a good way to, yeah. So here d by dz just forgets about epsilon entirely, doesn't interact at all, and we get this notion of the bracket here. So here d by dz can act on f and h. Sorry, there's a typo here. This should be, is there a typo? Sorry, there's no typo here. The overall sign here, this minus h dg dz and d by dz arises from moving this past this odd element epsilon, but yeah. And there should be another epsilon on this side, I'm sorry. There's a more important bracket, which is involving this odd vector field d by d epsilon. And what it says is that it can eat the formal parameter epsilon here. So the bracket of d by d epsilon was something that's like proportional to epsilon. Just pairs the epsilon with the d by d epsilon to get this overall even element f d by dz. So this is going to be the important one that we'll use later on. Okay. And the claim is that there's no problem in making this sort of sheaf theoretically. Everything is local to global. We get this nice sheaf of DG Lie algebras. So there's a very closely related factorization algebra associated to this sheaf of DG Lie algebras. And what it does on an open set, for some reason I'm just describing it on sigma equals C now. What it assigns to an open set U is the following. Well, I look at the value of the sheaf of Lie algebras on U, but I only look at its compactly supported sections. So I only look at sections that are compactly supported. Well, this is still a DG Lie algebra, and I can look at its Lie algebra chains computing the Lie algebra homology. So it's a very standard sort of result. This is, in the Behlens and Drinfeld terminology, this is called the sort of chiral enveloping algebra construction of a chiral algebra. And this was also made very precise by the work of Cassell and William to show that objects of this type always define a factorization algebra. And the sort of key fact for us is that, well, this factorization algebra is very interesting because if we apply this functor vert to it, we exactly get this topological Virasoro algebra out. So this is really a factorization algebra enhancement of the topological Virasoro vertex algebra. This is the first step in that goal that I sketched in the previous slide, is to construct this topological Virasoro vertex algebra at the level of factorization. So let me just say briefly how this goes, where these elements are, where the sort of generating elements we had on this side are coming from. So I'm going to tell you that there's these part of the data of the vertex algebra is to prescribe all of these families of endomorphisms depending on some integers. So let me tell you where those come from in the factorization side. Those come from actually looking at a special open set, namely the open set that's an annulus. And the factorization algebra that I described can be sort of simplified in the following way. So this all uses sort of some analytic data here. This data rho. Rho here is really it's a function. It's a smooth function on the annulus, which is identically 1 near the interior boundary of the annulus, and it's identically 0 near the exterior boundary of the annulus here. what this says is that its derivative, namely d bar of that function here, is actually a bump function. So it's actually compactly supported. So I'm going to use that to construct sort of explicit models of these elements of this factorization algebra. And how does it go? Well, I can take some vector field here on the punctured disk. That's really one of these like Laurent polynomial vector fields. Remember I was calling these L sub n in the vertex algebra world. And I get an element in my factorization algebra using rho in the following way. So all I do is I hit the bump function with this element, with this vector field, which is Ln. So this is an explicit way of realizing. And in fact, this inclusion sees almost everything on this side here. This is actually a dense inclusion up to cohomology. So you're really not missing much by just looking at these power series here, these Laurent polynomials here. And then there's a similar result just for the Debye complex, not adjoint vector fields, where I just have an inclusion of Laurent polynomials inside of here. Again, using this description in terms of bump functions. So using this, we can identify the sort of generating elements of this topological Virasoro in the following way. Well, where does this, we have these even vector fields here, just these ordinary holomorphic vector fields that's sitting on this side over here. Well, under this inclusion here in the functor that Costello and Guillaume defined, you can check that these define these L sub n's in the topological Virasoro. We also have these degree -1 elements. Those look like epsilons times some holomorphic vector field. Those are identified with G sub n. Then we have these degree +1 vector fields, these Zn's d by d epsilon. Those are Q sub n's. And then finally, this J sub n, which hasn't really played a role for us, you can identify with this even vector field that looks like epsilon d by d epsilon times some holomorphic function. So it's this type of correspondence is essential in actually proving this result, that the functor vert applied to the factorization algebra gives you these topological Virasoro algebra. But just wanted to give you a sort of geometric flavor for where these generators are coming from. Okay, I can probably finish in like 10 minutes. So here's the definition now of an n=2 factorization algebra, twisted n=2. Well, it's a holomorphic factorization algebra F. This is all happening just on flat space. So the Riemann surface here is just C. Together with a map of factorization algebras here. So this is this sort of chiral enveloping algebra that I just defined from the sheaf of Lie algebras. And I require the data of a map into my holomorphic factorization algebra F. This is exactly reminiscent of the way of defining a topological vertex algebra. I require the existence of such a realization of these twisted n=2 algebras inside of my factorization algebra. Okay. So sort of as an immediate corollary from this fact that I just sketched above, if I apply this functor vert to this subcategory, or this category of n=2 factorization algebras on C, I exactly land in the category of topological vertex algebras. So this is really the sense in which this notion of these twisted n=2 factorization algebras are enhancing the notion of a topological vertex algebra in the world of factorization algebras. Okay.
Brian, is the functor vert, this is Aaron, is the functor vert like strictly symmetric monoidal? Is that what is being used here?
I'm not using
so
that
that like
here.
Modules go to modules?
I'm not using that here. So I just require the existence of this map here. So I'm just using functoriality here.
I'll just pipe up. I thought that I So giving this map is stronger than giving an action.
It is. Yeah.
I don't know if that's relevant. Okay. Yeah.
Yeah, I can say a few more words about that maybe in a minute, but that's right. So all I'm doing is I've defined in both cases. Sorry, how do I go back? In both cases, I've defined the data of either a twisted n equals 2 thing or a topological thing as the data of a map of factorization algebras or a map of vertex algebras. So all I'm doing is literally applying the functor vert to this map of factorization algebras here.
Okay, yeah, I guess I mistakenly interpreted that as like an action map.
I see.
And you're saying that's not right.
It's more data than an action, I'm claiming. Yeah.
Okay.
Yeah. You could certainly formulate things in terms of actions and maybe get a wider class of n equals 2 factorization algebras. Sort of all the ones I care about arise in this way.
Okay, cool.
But it's a good question.
Thanks.
Yeah. Okay, so let me just remind you what was happening in the vertex world. Well, given a topological vertex algebra V, I could use this operator Q sub 0 to get a new DG vertex algebra in this way. Well, how is this working for factorization algebras? Well, it's quite similar. So this is sort of, might be a little technical construction, but it's, maybe I'll just go through it really quick. So let's look at this piece of the sheaf of DG Lie algebras spanned by this element, proportion to this element d by d epsilon. So namely, I want to look at the part of this sheaf that look like just Dolbeau forms on sigma, adjoin this odd vector field d by d epsilon. So this is actually a subsheaf. Great. Moreover, I have the following sequence of maps here. So these sequence of maps are going to depend on a complex number together with a holomorphic function. So I'll say what I mean by that in a sec. So what I'm doing is, well, this is a DG Lie algebra. I can look at its Lie algebra now. It's the Lie algebra cochains computing cohomology, just of the sub-Lie algebra. And since this parameter is odd, you can actually check that these cochains are identified with just the symmetric algebra on the dual of this space here. So this dual, I'm using sort of maybe notation that I haven't quite explained, but this is roughly like compactly supported 1 comma star forms now on the Riemann surface, but I have to put in distributional sections as well. This goes back to Ezra's point that I should really be careful about the topologicalness of all of my spaces involved. And here's my attempt at being careful with that. So from this, I can use the function f just to integrate against one of these. These are just distributions. I can integrate against any holomorphic function to get a number because they're compactly supported distributions. Well, that lands me, just applying it sort of term by term, it lands me in C, and I have the symmetric algebra in C. And then what I can do, viewing this just as a polynomial, I can evaluate this polynomial on mu, this number of mu, to get a number out. So what is all of this doing? Well, everything I just said here is completely local in the surface sigma. And it actually extends to a construction of a module of this trivial factorization algebra again on the right-hand side. So this is like a constant factorization algebra. And what I've done is I described the structure of a module for this factorization algebra on the left-hand side here. So what this does is this endows the constant factorization algebra, the structure of a module over this interesting factorization algebra here. I'm going to denote this thing by, so underline means constant factorization algebra, and it depends on these two pieces of data, mu and f. So how am I going to use this? How I'm going to use this is the following. So let's start with one of these n equals 2 factorization algebras, f. Well, in particular, it's a module for this sub-Lie algebra here. And I can look at cochains of the sub-Lie algebra generated by Bilbo forms d by d epsilon with values in F. This is again going to be a factorization algebra. Everything is local in space-time in the Riemann surface. It's a module for this cochains on just the sub-Lie algebra, just in the obvious way. But then I also described the constant factorization algebra with the structure of a module over the same thing. So I can look at this tensor product of factorization algebras. So what I'm doing is I'm really thinking of a way, what this is doing is this is really sort of specializing the factorization algebra F. You can think about it in that way. So why is that? Well, let's just do like a really, oh, and sorry, maybe there's a function F that was the input data before. Here I'm taking that holomorphic function F just to be the constant function. So I get the trivial module for that choice of a constant function here. So just to get a feel for what this is doing, notice that if I take this parameter mu to be 0, well, all I do is return the original factorization algebra here. It's not so hard to see. So what you can do is, what you can think of this construction as is, well, it's deforming F to something that I'm calling F tilde sub mu. It's deforming the differential. So it's sending the internal differential df to the internal differential, to a new internal differential that's d sub f plus d by d epsilon here. That's what this construction is doing. So this is our version of this DG vertex algebra from the world of topological vertex algebras. And here's the main theorem, and I think this is my last slide. Yes, here's the main theorem. As long as mu is not 0, because I know when mu is 0, I just get back the thing I started with. This F tilde sub mu satisfies the conditions of Elliott and Safronov to define a framed E2 algebra. So let me just sketch this proof and then I can finish. So already by assumption, F is a holomorphic factorization algebra. So I already know a lot of the translation, the anti-holomorphic translations act trivially, homotopically trivially. So that part of, so we're halfway there in verifying that it's a module for R2 de Rham, all translations in R2. What we need to see is that the holomorphic translations are also trivial. Well, to do that, I'm going to use that commutator that I wrote down in this DG Lie algebra. The sheaf of DG Lie algebra is Tn equals 2. So you remember I had this commutator d by d epsilon with epsilon d by dz. That gives d by dz. And why does this relation hold for F tilde? Well, it goes back to this way of thinking about this F tilde as really deforming my differential d sub f to d sub f plus d by d epsilon. So that's what gives rise to this homotopy here. We can use, or that's what gives rise to this relation here. I can use this explicit homotopy called epsilon d by dz. So that was part of their condition, as I need to know that translations actually descend to action by the de Rham stack of translations. So that tells me that. And then David made a very good point before, which is to verify this fact that the inclusions of a little disk inside of a bigger disk is a quasi. Well, you can actually appeal to another de Rham triviality of another Lie group, namely the Lie group of dilations. And well, that's not so hard anyway. That's not so hard here because, well, I have this, before I use this vector field epsilon d by dz, but in fact, I have a whole slew of vector fields of this form. Namely, I can multiply it by any holomorphic function. And I get the triviality of any holomorphic vector field, actually. So what this says is that actually the whole Lie algebra of holomorphic vector fields acts trivially on F tilde. So that's enough to know that dilations act trivially too. And that's a sketch of this fact here. So the goal that I had started with in the very beginning is sort of accomplished because now I can think about this F tilde sub mu as being an explicit cochain model for the BV algebra that Leon Zuckerman and others like Huang had developed. So yeah, I'll stop there.
Thank you, Brian, for that great conceptual talk. Are there any questions out there?
Sure. Shall I start? Yeah. So actually, it's the same question. So actually, I had a quick look at Costello-Guillem, and as far as I can work out, they're working with, let's say, the easy part is to introduce. They look at unbounded complexes of DVSs, which are essentially just some sort of vector spaces in the site or the smooth site.
Correct. Yeah.
And then they say that's a multi-category, and then they take the symmetric monoidal envelope of that. That's the only, I may be misreading what they're doing because they don't actually carefully examine symmetric monoidal structures in that appendix you referred to, but in the text. So
okay.
There's some kind of, okay, so if that's the case, and I'm not 100% sure it is, then the theorem you've proved is you've constructed a framed E2 algebra in that category, which I have to say is not a wildly familiar category to people who do homological algebra.
Okay.
And so my question is, do we have any particular functors out of that category that we can then test any of our regular notions? So I assume we can take cohomology and then we get back Leon Zuckerman.
Certainly, yeah, cohomology does.
So that much we can do. But sort of, for me, the most interesting aspect of E2 algebras is that they have Kossel duality. And certainly my intuition is that Kossel duality, even for commutative algebras, requires very strong connectedness hypotheses. So
sure,
I'm a bit concerned that the category that you've constructed a framed E2 algebra in is not a category for which that admits a decipherable understanding of Kossel duality. I mean, conceivably using some sort of presentability source, there is a statement, but it mightn't be a statement where you can work out what the category that the Kossel duality landed you in was. So I just wanted to ask all those questions. Do you have, can you unpack what I said and give me a map for where I should look for?
So I don't know if I can give you a precise map. I can definitely tell you, so these causal duality for the type of categories that we think about is been at least partially developed by Kevin in a different context. So there's at least like a nice...
Well, that's what always worries me. I mean, a different context is a different context.
Sure. So
I mean that's a fact that, these are very technical questions which require immense care. And so to develop the theory in a different context, but do all your constructions in yet another context, there's a bridge that needs to be built.
I completely agree. I would say that in the generality that I was talking today, I would not be able to produce sort of framed E2 algebras or E2 algebras in more familiar categories, but there are sort of connectivity assumptions you can put in on my side that does lend itself to maybe more familiar descriptions, but certainly not all the objects that in the generality I've talked about today. I do agree with you that there's not going to be a relationship, but so part of like what Kevin does with causal duality is to look at sort of a nice subcategory of the types of factorization algebras or E2 algebras that we cook up and studies causal duality there, and shows it sort of coincides with the usual.
Yeah, but that's exactly the usual situation that,
sure.
That you can write down the functors for general differential graded, positively graded cochain differential graded commutative algebras, but
yes.
It's only if you have a nilpotence condition that you
I
get
totally
duality.
Yeah. I totally
agree.
Yeah.
That's, to me, these are the sort of main issues. What kind of topology is lurking on these cochain complexes, which make them which make formulas that one has in topological field theory converge?
I see. No, the points taken. Yeah, I don't have like a general solution for the I don't have a general solution right now, but
so as you know, moving forward, I would suggest that as a possibility to make sure that your functor lands in a category which is amenable to some kind of structural statement, perhaps not Kossel duality. It would be very nice if it would be optimal if it was, but not necessarily. But so, at least that there are several functors out of it.
Yes, yeah, that's right.
That do more than reproduce Lian-Zuckerman.
I see. Okay, that's a good suggestion. The points taken. Yeah. Thank you.
Any other questions? Yeah, Chris.
Yeah, so I just want to make sure I understand your kind of final point here. So are all the F mu's away from 0 supposed to be isomorphic or something? Because you kind of wanted to make a functor or something like that.
They all are isomorphic away from u. Yeah. So 0 is just the special point, but they're generically isomorphic. Yeah.
Okay. And then you'd mentioned kind of this topological field theory in the beginning, and I'm not sure if it appeared again later.
Yes.
So, yeah.
Very good question. So these F sum mu's here that I just defined can be thought of as the observables of some topological field theory as well. So you can, there's a different construction of these F sum mu's which sort of uses a different set of tools, namely like what's called supersymmetric twisting that produces factorization algebras of this type. The reason this is sort of nice is because I didn't have to specialize myself to an actual topological field theory or chiral conformal field theory. I just started with a general factorization algebra. But in practice, these do agree with sort of the factorization algebras underlying a lot of the familiar TFTs that you know of, yeah, in special examples.
So what dimension are you talking about here?
This is all about 2D TFTs. So these are all
TFT, okay.
Chiral CFTs possibly deforming to 2D TFTs. That's right.
Okay. All right. Thanks.
Yeah.
Oh, could I ask?
Are there other questions?
Yeah, another quick question. So you mentioned in the introduction the ghost sector. Have you constructed the ghost sector as an n=2 factorization algebra that you can apply this construction to?
Yes, that's my main application in the immediate future, actually. Yeah.
Yeah. So you have, in this rather mysterious infinity, symmetric monodal infinity category, the symmetric monodal envelope of the multi-category of unbounded chain cochain complexes of DVSs, you have a frame D2 algebra.
Correct. Yes.
With, if I remember right, with central extension -3.
I mean, yes, yeah, that's right.
Yeah. Yeah. Right. Okay. Yeah. Mm-hmm. Cool. Okay. Have you been able to couple it to anything?
Couple.
I mean, that is, can you construct the semi-infinite cohomology?
When I said string vertex algebra, I really meant the semi-infinite cohomology already.
So for you, the factorization algebra already had the ghost sector.
Exactly. Yeah. Okay. That's just my term. Maybe that's not standard terminology, but that's my.
That's okay. Right. Okay. So the cohomology would be a kind of double. It's a hypercohomology incorporating semi-infinite and whatever other cohomology you had kicking around already.
Precisely. Yeah.
I had a question, Brian. It's John Francis.
Hey, John. Hey.
So in that field theory, you said that you got a factorization algebra on the target, X, like at the very beginning, like that it was like maps from sigma to X or M, and you got a factorization algebra on the target, right?
So maybe I should have been clear. I wasn't claiming that I get a factorization algebra on the target. What I do get is a BV algebra, which one can then take and turn into a sort of QFT if they want. So I don't have a general story here, but in practice, what you get out of these like sort of string vertex algebras objects that actually do behave locally on the target. But I don't have sort of a general reason why this is true. So what I would say is that the string vertex algebras that I cook up, they are what they are in the target. They may just be some very complicated sheaves, but at the end of the day, what I find is they actually admit these nice local descriptions, which you can then in turn into a factorization algebra. But that sort of works example by example for me right now. I don't have like a general procedure for that. So sorry if that was, I didn't mean to like claim more than I.
No. So I guess my question was going to be, and then maybe still is, then if this is describing some kind of a sigma model of infinitesimal maps, because obviously if you just take a mapping space, that's not going to be local in the target. But if you force it to be local in the target, it's like considering, maps that are very small from the source, and so I guess I was wondering if that was the field theory on the target that you were getting, where you force locality in the target and get null homotopic or small infinitesimal maps from the source.
Yeah, John, that's exactly right. I'm only looking infinitesimally for now. That's right. That's exactly right.
And is that also the case with the chiral differential operators that you mentioned? Are they
That's
also
correct. Yeah, chiral differential operators are also about infinitesimal maps. Yeah.
John, are you going to join us in the tea room?
Yeah, so on that point.
Only questions for Brian right here.
But I want to say something. If you're not joining us, then I have a comment I'd like to make. But if you're joining us, I'll wait till we get to the tea room.
So on that point, you might notice in the chat room, or in the chat box, a link to the tea room. And everyone's welcome to join us there. Brian, you're obviously the person of the hour. If you could join us there, that'd be great for some more informal discussion. Okay. Thanks again, Brian, for the great talk.
Yeah, thank you.